so we're going to play some more with vectors. And I don't know about you guys, but when I discovered vectors, I started thinking about them all the time. And I discovered vectors about the time I got into bicycling. And so I always wondered things about Gary's biking along. Here's his bicycle. Oh, that didn't go right. Something like that. Here's me flying down the road. And then I hit a rock and I go flying off the bicycle, right? And I have a helmet, so don't worry. And I'm going to hit the ground, right? Now there's a bunch of things going on, but I got force vectors going on. I'm heading in this direction, and there's a horizontal force going on, and there's a vertical force going on there. And when I hit the ground here, what parts of those forces are going to have effects on me? And when you think about that, kind of draw this vector, and it whacks the ground there. What's going to happen here is I'm going to have a projection of the force going on that hits the ground. It's not the whole force that affects me, right? In terms of like sliding. So projection of vectors is kind of important. In addition, if I'm towing something, like I have a little red wagon at home. Oh, it's not red. Let's make it red. There we go. So I have a little red rag. Oh, did I just mess that up again? There we go. Okay. And I pull my little red wagon down the street with some force. It goes that way, right? From whatever point P I start at, P to some point Q over there. And the force I'm giving it, the whole force isn't applied to me pulling it, is it? Because I am pulling up on this thing. So what happens in that case is this vector, you can consider it being projected downward, and only that part of the force is actually working to move that object right there. So vector projections are all over the place in terms of the way things interact with each other. And so we're just going to look at a mathematical definition of what a vector projection is, which you guys already know whether you've seen it or not before, because you know basic trigonometry. And that's all it is a consequence of. And then there happens to be this magic relation that pops up in addition to it. So let's move on to some math to get, then we'll come back to those applications. So reminder about vectors. I know you guys like the hat notation, but I have years of math teachers putting the little arrow over the top. So I'll often slip and write that, but both of those mean a vector. In 3 dimensions, which we'll use here and there, you know, we're going to have an A value, a B value, and a C value for the vector. But it could be a 2D vector too, in which case we only have X and Y to worry about. We talked before about the magnitude of a vector. And we usually use the word magnitude instead of length because it could mean something else besides a distance vector. It could be a force vector or something else. And the magnitude is just distance, really. So that's just a squared plus b squared plus c squared, Pythagorean theorem in 3D. And we usually write magnitude. You'll see it a couple of different ways. Sometimes it'll look like just absolute value bars for the vector. Other times you'll see a double set of bars to distinguish it from absolute value. So you'll see either of those definitions for magnitude or notations for magnitude. Another thing I talked briefly about last time, but I didn't do too much with, is the idea of a unit vector. In the direction of some given vector v. Vector v is going to have some distance, and that distance is generally not going to be a distance of 1. Okay, so what we do is if we take any given vector and we divide by its length, if you think about that, when we apply the distance formula, we're going to have this distance divided by itself, and so we're going to force a length of 1 on the vector by dividing by its size. Okay? So this right here is called a unit vector in the direction of v. And all you do is you take your vector and you divide by its length, or its magnitude. Okay? And sometimes we don't need to know a distance or a power or a force. We just need to know which direction are we facing, and I only want that value to be have a value of 1 in terms of its magnitude. So we're going to need that later also. All right, next popular topic, let's see. We'll get back to 3D in a second. Let's talk about, we looked at addition of vectors, subtraction of vectors, we looked at scalar multiplication. When it comes to multiplying two vectors, there's a lot of ways to define multiplication. One way to define multiplication is what's called a dot product. And the dot product of two vectors, let's say we got vector v dot vector u. So v has coordinates, let's say v1 and v2, dotted with u has coordinates u1 and u2. Then the dot product is defined by taking the product of the x components, so the first components, so that would be v1 times u1 plus then the product of the second components added on, v2 plus u2 times u2, sorry. Let's see, did I have a good example? Not really. So let's suppose if we're looking in 2 dimensions and we take the vector 2, 1, and then let's take the vector, how about 3, 4, 3, 5. 1, 2, 3, 4, 5 is going to be somewhere up here, so we have that vector. So the dot product for these two vectors, so let's say this is my vector v, and this one's my vector u. So u dot v or v dot u, order doesn't matter here because of the arithmetic involved. It's just going to be 2 times 3, which is what, 6, and 5 times 1, which is 5. And so it's going to be 11 is the value of the dot product. So we'll look at uses of that dot product in just a moment. So let's see. What else did I want to say about that? Yeah, that's worth noting. All right. So what happens if we dot a vector with itself, like v dotted with v? So I had the vector v was 3, 5. So that's going to be 3 times 3, which is 9, plus 5 times 5, which is 25, which altogether gives me what, 34? The 9 basically came from taking the 3 and squaring it. The 5 came from taking the 25 from the 5 and squaring it. Doesn't that look familiar? 3 squared plus 5 squared? That's the Pythagorean theorem without the square root. So when we dot a vector with itself, what we end up is we get the magnitude of the vector squared. So that's something to know. If a vector is dotted with itself, then you have the magnitude squared. So we could also say the magnitude of the vector is equal to the square root of its dot product with itself. And then next class, we'll get to another definition of how we might multiply two vectors and see what the output might look like. Now, there's another definition of the dot product that pops up. And the alternate definition of the dot product for u times v, or u dot v, excuse me, is to calculate the magnitude of u, multiply that by the magnitude of v, and then multiply by the cosine of the angle between them. Can you think of another instance in math that you saw something where you have the product of two numbers multiplied by a cosine of an angle between them? Does that look at all familiar? So here's a hint. If I draw this vector in right there, that would be the vector u minus v. And when I do that, I have formed what kind of shape? A triangle. Yeah. And if I label these magnitudes, maybe we can stick with red. Let's just call them A, B, and C. There's a relationship between A, B, C, and theta. Anybody remember what it is? If it were a right triangle and theta was 90 degrees, then we would have A squared plus B squared equals C squared. Right, but did I say anything about this being a right triangle? Nope, I didn't. So turns out there's a fudge factor you can throw in there. If from the A squared, B squared, you subtract off A times B times the cosine of the angle between them, then that adjusts. So this is kind of a generalized Pythagorean theorem, which goes by another name as the law of cosines. Yeah, this is the law of cosines. So it turns out the alternative definition of the dot product comes from the law of cosines. Okay, so I'm going to skip the algebra behind it. It's in the book if you want to read that part. It's not all that exciting, but it's just a consequence of the law of cosines, which is kind of neat. So we have these two different ways to look at the dot product. We have this pairwise multiplication of components, then we add them together, or we have the magnitude of each vector multiplied times the cosine of the angle between them. So two different ways to define the dot product, which is kind of cool. Okay, next. So dot product is going to be powerful. Consider, excuse me, consider the idea of the wagon I was talking about a minute ago. So we have, let's say we have this vector right here. Let's call that vector B. And then we're going to have this other vector. Let's say that one right there. Let's call that vector A. And sorry, I can't bring myself to draw any hats today. We're stuck with arrows, but you can draw hats all day long. I'll know what you're talking about. Let's say vector B is parallel to x-axis. So vector B could be something like the vector 5, 0, just for fun. And let's say the vector A is something like the vector 3, 2, maybe. That looks about right on this picture. I could draw a perpendicular line down here and consider what is the length. Like if a shadow were cast by A straight down onto vector B, what would it look like? Well, if we know this angle in between here, let's call that theta. This is just a right triangle, true? So we know, let's see, adjacent sides are related to what trig function? Cosine. So this should be whatever the length of A is, what we call the length of A, that, its magnitude, times the cosine of theta. True? And that's how we define this. And I'm just calling it an X component here, but I could rotate this in space and it would be something else, right? So at the moment, that's what we call how we calculate the X value based on the angle and the blue radius there, or the blue magnitude. Now, B has some length. Would you agree it's not 1? You know, sometimes the length of a vector is 1, but most often it's not. Now we know what the length of B is. That one's pretty straightforward. But if I want to create a new vector in the direction of B, but based on an interaction here with the vector A, well, don't I know how long this new vector is already? Okay, we call this part right here the length of the projection. So we're getting into vector projections now. So that's the length of the projection. Sometimes it's just called the scalar for the projection. If I want to turn this length into a vector, all I have to do is point it in the right direction, right? Well, which vector is pointing in the right direction? Well, B is pointing in the right direction. However, B could be too long or too short. I want to make sure I end up with the right size. So how do I adjust B? Well, I make it a unit vector. How do you make something a unit vector? You just divide by its length. So then I just divide B by its length. And what this entire thing together is, this is the projection of A onto B. Now that's a lot of English for a math person, so usually we abbreviate that. So the abbreviation is projection, P-R-O-J, of A onto B, like that. I get lazy sometimes and forget to write in the little vector hat or arrow, whichever you prefer. So the projection of V onto A. The projection is a vector. Okay. Sometimes we're only concerned about the magnitude of that projection, like in terms of force when I'm pulling that wagon. I know what direction it's going. I only care how much force is getting applied. So that's what the black part would be. And then the red part gives me the direction of that projection. So I'm going to tweak this a little bit. Okay, because don't you see some familiar components based on our previous set of notes, right? Back here, when I gave that alternate definition, I have a cosine and I have the magnitude of those two vectors. When I look up here, well, there's my cosine, there's the magnitude of one vector, but the magnitude of the other vector is in a different place. So if I just tweak this a little bit, so let me just rewrite this on a new page. So one way to define the projection of A onto B is to take the magnitude of A times the angle between the two vectors I'm looking at, and then to multiply that by the vector B. So I have this first black part as a scalar times a vector divided by another scalar. So that's the definition we just came up with for a scalar projection. Now, what I would like this to do is look more like the dot product, because the dot product's pretty nice. So I'm just going to sneak in here and I'm going to say, well, let's just multiply in next to that A, the magnitude of B. Now, if I just multiply that in, I have a whole new different vector. It's longer than it used to be. So I should also divide it out down here. The cosine was hanging out there. And then we still have this other B vector divided by its magnitude. So the only thing I'm doing here is I'm multiplying and dividing by the magnitude of B. The reason I'm doing that is because now this part right here is just the dot product of A and B. So now I'm redefining the projection of A onto B by saying, well, just calculate the dot product however you want. Could be the pairwise multiplication and add them up, or it could be the other way I have listed up here. And then we're going to have B over the magnitude of B. Now, keep in mind, we still have this other magnitude of B hanging out over here. And so usually they'll get all put together. And it'll be written as A dot B over the magnitude of B squared times the vector B. And this part here is just some number that we calculate. Dot product leads to a number, not a vector. Magnitude of V is a number, not a vector. Okay. So this is just an alternate way to come up with the value of that projection. Okay. Some people think this version over here is the easier one. Some people think that version above is the easier one. I don't know, take your own pick. I like the one above better because this part right here is the magnitude of the projection, which is what I often want in like a physical application. Yeah, I want the direction. Well, here's the direction right there, but that's the magnitude of the projection. Now keep in mind, in the formula below, I move that magnitude into this one right here. So this constant out front in the bottom here, that's no longer the magnitude of the projection. You with me? Because I moved that guy over. Okay. So there's a few things to keep in mind. Sometimes we want the magnitude of the projection. Okay, take the magnitude of the projection. No big deal. And there's a couple ways to get that. But we have two different definitions for the projection, and you can take your pick as to which one you want. Okay, so what else do I want to do with this? All right. Next, we're going to play around with that in a couple of different ways. So there's lots of applications for projections of vectors, and those projections involve the dot product. Remember, the dot product can be defined in a couple of different ways. So U dot V can either be said to be U1 times V1 plus U2 times V2, or it's the magnitude of U times the magnitude of V times the angle between them. So here is one possible application of that. Suppose I have f of x, and let's let f of x equal x cubed plus 3. And then we're going to take g of x, oops, wrong color, to be 3 minus x squared, excuse me. And what I want to do is I want to find the angle of their intersection. Intersection, there we go. Now, since this is a parabola, it heads down in two directions, then it's likely to hit the cubic function more than once. And I am concerned about the intersection at 1, 2. Is that right? No, that's not right. That doesn't work, does it? They don't meet at 1, 2. Did I write this down wrong? F of 1 is 4, not 2. Oops. Maybe I meant f of x cubed plus 1. Then they meet there. Let's try that. Let's see, now they both have the point 1, 2 on them, right? All right, so let's make a quick sketch of those, make sure they meet at that point, see what they look like. So let's see, x cubed plus 1, that should be, and that one's going to be in black. So it's going to have kind of a central point here and a point there and a point there, and it is going to wiggle through those points like that. And then 3 minus x squared, so 1, 2, 3. Oops, that's positive 1, sorry, and negative 1. That's going to have a vertex here and a point over 1, down 1, over 1, down 1, over 2, down 4 is going to be somewhere over there. Oops. So it looks something like that. And we want to know what's going on at that intersection. Now, to figure that out, I need to know their tangent lines, right? So this guy has a tangent line. Maybe it looks something like that right there. This guy has a tangent line. Maybe it looks something like that right there. When two lines intersect, as long as the lines aren't in the same direction, there's more than one angle formed, true? Okay, so we got to keep that in mind. There's two different angles formed here. We've got this angle right here, and we have this angle right there. And those two angles are always going to be supplementary. So if I call this one alpha and this one beta, I know that alpha plus beta has to equal pi. They're called supplementary angles. They add up to pi or 180. Supplementary. And so then the question is, when we play with this, which angle are we going to get? And which angle do we want? And which angle we want is, it kind of just depends on like the direction of travel. If we were considering this the direction of two moving objects. So is finding the tangent line an easy problem? It's not too bad. Okay, so here we have two tangent lines to find. Once we find them, then we have to play around to get their angle of intersection. However, if I think about this just a little bit differently, and I think instead that from that intersection point, let's use a different color, I'm going to generate a vector. And I'm going to generate another vector. Given two vectors, do we have a way to find the angle between them? Yeah, we've got the dot product here. So once I have those two vectors, it's not so bad. Well, what designates a vector on a line? Well, really all I need is the slope, right? Because the vectors, I don't care how long it is, I just need the direction to go, and the slope tells me that. So all I have to do is find the slopes of each of these tangent lines. I don't need the whole tangent line. All I need is the slopes. Once I have the slopes, I can find the angle between. So that's the trick here. So let's do that. Let's find f prime of x and g prime of x. So we have f of x is x cubed plus 1. So f prime of x is equal to 3x. And I'm interested with the point squared. Oops, yep, squared, thank you. I'm interested in the point 1, 2. So then my slope is just 3. If the slope is 3, I could think about that as a fraction, like 3 over 1. That implies I could use the vector where x moves once and y moves 3 times. So that would be a vector with that slope. Agreed? Because this is change in x, that's change in y. So from any point, that's moving in that direction. Okay. Let's work on g. G of x is, that was 3 minus x squared, right? And so g prime is going to be negative 2x. And so the slope at the point we're interested in should just be negative 2. Using a similar idea, I can generate a vector out of that, as I could say it's the vector 1, negative 2. So I need two things out of these vectors. So I need to put the connection together. The dot product says that if you take, let's say this guy right up here, what color am I using? Let's call this one our U, and we'll call this one down here our V vector. then if I take u and I dot it with v, that's going to be equal to the magnitude of u times the magnitude of v times the cosine of the angle. Now, since I have the coordinate values of these vectors, I can easily figure out the dot product and the magnitude of each, and then I can solve for the angle from there. So let's calculate each of those. So we need to know, what is u dot v? Well, u dot v, that would be 1 times 1 plus negative 2 times 3. So I'm going to have a 1 minus 6, which is a negative 5. On the other side of this equation, I need the magnitude of each. So let's see, 1 squared plus 3 squared is 10. So I have the square root of 10 for u. And then 1 squared plus negative 2 squared is 5. So I have the square root of 5 times the cosine of theta. So all I have to do is divide those square roots to the other side and take the arc cosine. So let's do that and see what we get. So new page. Theta is going to be the arc cosine of negative 5 over the square root of 10 times 5, which is 50. I'm not too worried about cleaning that up. It's not going to come out to be a nice number. Why bother? Let's get a number on that. So Google Calculator. Did I make a mistake? Oh, yeah, I could clean it up. Oh, it's just negative 1 over square root of 2, isn't it, when it cleans up? Yeah, nice job. Okay. Okay, so sometimes it's fun to clean it up. So negative 1 divided by the square root of 2. So I'm getting about 2.356, and that's radians, right? So we're getting a radian angle here. If I needed to put that in degrees, I could multiply by 180 over pi, would throw me into degree mode. So I'm going to go to 3 decimal places, 2.356 radians. And so I just want to explore my picture and see if that looks all right. So I'm going to use GeoGebra for that, because GeoGebra does very nice sketches and tangent lines and angles. So let's start GeoGebra. Okay, so let's see. I had f was x cubed plus 1, and g was 3 minus x squared. All right, so there's my intersection point. So I'm going to say, hey, GeoGebra, tell me where they meet. And it says they meet at 1, 2. Now, GeoGebra has this other awesome feature about making lines. It says, hey, would you like a tangent line to something? So, yeah, GeoGebra, I'd love a tangent line. So for the tangent line, you just click the point you want the tangency and the thing you want to be tangent to. Point you want the tangency, thing you want the tangent to. Kind of nice. And then I can ask GeoGebra to find the angle between those two lines for me. And it's got an angle measuring tool here. So I think if I just click those two, ooh, it gave me the wrong angle. I didn't want that one. Bottom one, then the top one. Oh yeah, order matters here, right? Which one will that give me? Okay, so it's about 135 degrees, and I didn't check to see. If I take this times 180 divided by pi, I get about 135 degrees. Oh, I get exactly 135 degrees. Oh, because it's 1 over the square root of 2. Oh my gosh. What are the odds of that? Like 0? All right. Where the heck did I go? Oh, there we go. All right, so we found it. And the dot product gave us a pretty slick, fast way to find that, which is kind of nice. All I had to do is find the derivative functions, the slope functions, and then plug in the x value. Didn't even matter what the y value was, because I needed the directions. What direction was each one heading? Now, in the homework problem, it's going to ask you for a acute angle of intersection. So there's 2 angles when these tangent lines intersect. There's that one right there, and then there's this other one there. So I would have to take pi minus or 180 minus to get the other angle. So just keep that in mind. It depends how the lines meet. Sometimes you get the acute angle right away. It just depends. So just pay attention to that when you do. There's a problem just like this in the homework. Okay, let's see. Another cool thing we can do with projections. There's an idea called orthogonal and normal vectors. So first I'll mention the idea of a normal vector. Normal vector is perpendicular to something. So suppose I had the line y equals 1/2 x plus 1 for simplicity. Quick sketch of that line. From 1, we can go up 1 over 2 and get another point, or down 1 and over 2 to get another point. So there's that line right there. That's the slope-intercept form. I could put it in standard form by multiplying everything by 2 and bringing x to the other side. So if I double everything, I'll end up with a 2y. I'll end up with a 1x, which I'm going to subtract over, and I'll end up with a 2 on the other side. Typically, when you put something in standard form, you write the x first. You put it in alphabetical order. So this would be negative 1x. Plus 2y equals 2. And a cool thing about lines in standard form, a normal vector for this line right here comes from the standard form. So I'm going to say vector n is going to be equal to negative 1, 2. And so if I pick any point on this line, let's say the point 2, 2, and I move according to the normal vector, or I stick the normal vector at that point, the normal vector says go 1 this way and then 1, 2 up. And so the normal vector is going to be right there. What's the slope of the normal vector? Well, isn't it just 2 over negative 1? Right, so the normal vector has slope 2 over negative 1, which is negative 2. What's the slope of my line? It's 1/2. You remember way back from like algebra 1, how are the slopes of perpendicular lines related? They're negative reciprocals, yeah. So when we put something in standard form, we get the opposite of the slope, opposite sign of the slope on the other side. We then take the change in x and we multiply that over to the y. So when you put something in standard form in alphabetical order, these two coefficients have to give you the normal vector. Just because of the arithmetic that happened, you're always going to end up with a negative reciprocal there, which is kind of nice. So anytime you have lines involved, standard form of the line always tells you what the normal vector for the line looks like. Okay. Now, sometimes we care about that direction and we don't care about the length. So sometimes we will normalize the normal vector, which means to make it a unit vector. Okay, so often we'll see that. So usually we'll go next and find the magnitude of this vector, which would be what, square root of 5. Okay, so the unit normal vector here, let's write it in blue up above. Come on. Unit normal for this situation would be, I could say 1 over the square root of 5 times the vector negative 1, 2. Or bringing it into a single vector would be negative 1 over square root of 5, 2 over square root of 5. Most homework problems in my open math don't worry about rationalizing the denominator. Rationalizing the denominator is sometimes important in algebra, but usually with numbers it's not important. So I like it in that form right there. All right, so next idea. So normal just means a vector perpendicular to something. If the thing is a line, then normal is always the same. If you think about a parabola, the normal vector is going to change depending on which point you're on that parabola. So on this parabola, right here, the normal vector might look like that. Over here, the normal vector straight up. Here, the normal vector looks like that. Okay. All right, so new page, orthogonal vectors. Orthogonal vectors are just perpendicular vectors. If two vectors are perpendicular, what's the angle between them? Right, we have 90 degrees or pi over 2. So theta equals pi over 2 is the angle between. What is the cosine of pi over 2? It's 0, right? Well, when we take the dot product of two vectors, one formula for the dot product is the magnitude of the vectors times the cosine of the angle between them. So what that means is anytime you have perpendicular / orthogonal vectors, you know that the dot product has to be 0 because the cosine of the angle between is 0. So in the previous example, we had a pair of vectors, but yeah, we could just use those. We had, if we look at the slope of this line right here, the slope gives us the vector 2, 1. Oops, where did I go? Oh, right here. So let's say we have the vector 2, 1. We calculated the normal to that. Normal means get a perpendicular vector, right? And one version of that normal vector was the vector -1, 2, wasn't it? And so if I dot those two vectors, so anytime you see a vectors with a dot in between them, it's the dot product. We can use the component-wise dot product, which says take 2 times -1, add that to 1 times 2, and we definitely have a 0. So either way you calculate it, right, it's got to agree. So this gives me a way to check to see if two vectors are orthogonal. Okay, so I'm just going to give us a pair of 3D vectors, and we're going to check to see if they're orthogonal. Okay, so I have the vector P, which is 1, 0, 5, and I have the vector Q in 3D, which is 10, 3, -2. And so if I dot those two vectors, what do I get? Well, I get 1 times 10 plus 3 times 0 plus 5 times -2. So yeah, it definitely comes out to be 0. So that means if we plot these in 3 dimensions, we should see that they meet at a 90-degree angle. So I'm just going to do that quick, and then we're out of time. So GeoGebra doesn't do 3D graphing, neither does Desmos. So Wolfram Alpha will. I don't think, do they? In Desmos? Okay, I couldn't figure out how to do 3D vectors in Desmos. So to do a vector in Wolfram Alpha, you just type vector, curly bracket, and then your vector. So what did I have? I had 1, 0, 5. Oops. And then I think if I put a comma, it'll graph both of them. Vector 10, 3, -2. You did a 3D plot in GeoGebra? Okay, I'll have to look that up again. I couldn't make it work before class, so I wasn't looking in the right spot. So if I hit enter, graph those guys for me. And will this one let me rotate it? Let's see. You can, okay, so I gotta figure out how to do that in GeoGebra then. What if I open code here? Will it graph them here for me? Come on, graph. Okay. Apparently I have some more research to do. I could have sworn I did this earlier. All right, we'll come back to this next class then. And I lost my picture. Anyway, they do meet at a right angle. So in 2 dimensions is not too bad to do, but 3 dimensions is a little trickier. But here's the catch as to why this works in 3 dimensions. If you take any 2 vectors in a 3D world, so here's my z-axis, x-axis is usually that one, y-axis is that one. So maybe I have a vector that goes over 3 units that way, and then 2 units that way, and then maybe it goes 1 unit up. So that vector would be right there, 3, 2, 1. And then I make another vector. Let's suppose I go out 1 unit, and then 2 units, and then I go 3 units up. So that could be the vector 1, 2, oops, 2, 3. Now there's nothing special about 1, 2, 3. They were just easier to plot for me right now. And so that would be that vector right there. Anytime you have 2 vectors, they form a plane, as long as they're not in the same direction. So any 2 non-parallel vectors form a plane. Well, if I'm on a plane, right, we're used to plane geometry. So if I'm on a plane, the law of cosines has to work. If the law of cosines has to work, then the dot product has to find the angle between those 2 vectors, which is going to live in the plane the vectors live. It's got to, sweeping from one to the other. Okay. Visualizing that is the hard part. So I'll do a better job tomorrow of coming up with some visualization software. If you guys get a chance tonight, look around for something, and then we can come back tomorrow and do some more calculations, 3D, and visualize them. All right, have fun, do good math.